Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be talking about ionic bonds, alright? And as we look down here, this is kind of a review from what we've talked about in the last chapter. Okay, the last chapter, we should have been able to write out our electron configurations for atoms, be able to draw their dot structures, and understand, and this is using the Bohr model, to describe where electrons are found at different energy levels. Okay, so this should be kind of review. And we want to introduce the idea of the octet rule. So the octet rule states that atoms tend to form bonds so that each atom has 8 electrons. Okay? And you'll notice that at the end of the periodic table, the noble gases, they have full octets. So if you look here at the last energy level, which is energy level 3, we have 2 and 6. We have 8 electrons, and we have a full octet in the noble gases. So noble gases tend to not want to react with things very often. Okay, rarely do they react with other things. That's why it is safe. I mean, that's not just safe, but when you breathe in helium from a balloon, it doesn't start reacting with the air or other things in your lungs because it doesn't want to react with anything. Okay, in general. Okay, but for the most part, the reason why we are talking about the noble gases is because they don't want to react with anything. They have their full octets. But what about the rest of the atoms in the table? Okay, the other atoms are not like nobles. Okay, you can think of it kind of like those storybooks, right? Where the nobles, right? They're given everything in life. Everything is given to them. They are given status without having to earn it. Okay, it's just inherent within their rights, I guess, of being a king or a queen, right? So nobles already have full octets, but everyone else, if they want to be like a noble, they have to make some changes to their lives in order to reach this full octet. So keep in mind, these atoms, all the other atoms besides the nobles, are going to make changes, meaning they are going to either give or take electrons in order to have a full octet. All right? All right, so let's go over here and let's examine this with this image here. Okay? So if we look at the left side of the table, right? So we have the alkali metals and alkali earth metals. They tend to give electrons away, and they're going to form a positive charge. Okay, so we call them cations. Okay, so if they lose electrons, just say magnesium here loses 2 electrons, it now has a configuration that's like neons, right? It looks like neons. So if magnesium here loses electrons, it loses 2, its configuration now has 10 electrons, and it looks like neon. Okay, it's made a change. It's given its electrons away. But the difference between magnesium and neon is that magnesium has 2 extra protons. And those 2 extra protons we recognize as a positive charge. That overall, there's more positivity than negativity, so they're going to be 2 positive. All right? And if it's in the alkali metals, including lithium, sodium, potassium, they're going to be losing just 1 electron, so they're going to only have a +1 charge. Okay, and these are trends that you will see. In nature, you will find these elements losing electrons. They're not going to be found neutral in nature. Very rarely are you going to find sodium with all 11 electrons. It's probably lost its 1 electron. It's going to have a positive charge. Okay. Now on the flip side of the chart, okay, closer to the noble gases, it's easier for these elements to just gain electrons to have a full octet. Okay, so for example, chlorine, it needs 1 more to become like its next element, which is argon. Okay, you can't see it on this page, but argon is right here. Okay, so for it to become like argon's configuration, it needs to gain an electron, so now it has a full octet. You can see down here that chlorine has a full octet, and it has a negative charge. All right, when I'm saying this, they're not turning into argon, its configuration, its electrons looks like argons. But the number of protons is still chlorine, right? It still has 17 protons. Okay. All right, hopefully this can come together for you. If you can't quite understand it, I want you to read through this, and if you need to talk to me, we can. Okay. I'm going to keep going in the chapter. But the idea is we have givers and takers, and they want to have electron configurations that match our noble gas peers on the very far side. Okay. All right, so let's actually describe what an ionic bond looks like. Okay, an ionic bond forms when metals and nonmetals react to produce an ionic compound. Let me make a point here too. All right, if we look at our periodic table, the metal side of the periodic table, and then we have the nonmetals over here. Nonmetals tend to be takers, and metals tend to be givers. So let's just keep that in mind, all right? So it says right here, metals and nonmetals, right? We're talking about, for example, sodium and chlorine. Sodium is a metal, and chlorine is a nonmetal, right? And they're going to give and take electrons from each other, all right? And here's another thing to the ionic compound. It is electrically neutral compound made of cations and anions. Okay, so because they now have charges, they actually can combine, and they now form something that's neutral because they cancel each other out. So let's think about this. Sodium wants to give its one electron away, and chlorine wants to take it. It's in a relationship where it wants to give, and this one wants to take. And when it does that, sodium now has a positive charge, and chlorine now has a negative charge. Okay, this has a full octet because it lost an electron, and this now has a full octet because it gained one. And now they're going to be attracted to each other because sodium and chlorine are now positive and negative. All right, and now because of their charge differences, they are going to be attracted, and they form a neutral compound. And this is how we would draw it in an electron dot structure. The reason sodium doesn't have that one electron anymore is because it got taken by chlorine, and chlorine's now more negative because it has more electrons. Okay. This image here describes very well what is expected to be understood about ionic bonds. I would suggest for you to write this into your notes. We're going to draw it in class. Okay, please draw this picture and understand the mechanism that's causing this to happen. Okay, all right. Well, I can brush on this lightly. Okay, I actually have some over here. Let me grab some crystals. There's a good piece to look at. All right, so this is a salt crystal. I have them in class, and you can look at them. And if you look here, it's kind of hard to see with the white background, that they form kind of a cube shape. All right, and this one's a nice square. All right, this is salt that was put in water, and it dissolved. And then this water was slowly evaporated out, and these crystals formed. Okay, it looks something like this. Now, the crystal lattice is an orderly repeating three-dimensional pattern. So if you think about this, these pictures here that I'm showing you, this is just two of them put together. But when we work with atoms, we work with large numbers of atoms, and they actually make arrangements that make this cube shape. All right, and different ionic bonds are going to form different shapes based on their unit cells and how they align. And I'll talk more about that later. But the idea here is a crystal lattice is an orderly repeating pattern, okay, when they form these types of ionic bonds, and it happens to form a cube shape for NaCl. Okay. Now let's talk a little bit about bond strengths and regarding Coulomb's law. So there's those two factors with Coulomb's law, right? It's the size of the charge and the distance between the atoms, okay? And if we know the distance between the atoms and we know that they're charges, we can actually kind of determine some of their properties. So for example, sodium chloride, its distance is 276 picometers, all right, between these two dots, right? And they have relatively +1, -1 charges, okay? Now let's compare it to lithium chloride and magnesium oxide. Lithium and sodium both have the same charges, but lithium is a much smaller atom, and it's much closer to chlorine than sodium is to chlorine. So its distance is shorter, and because its distance is shorter, it forms a stronger, tighter bond because of its distance, okay? In this example, we have magnesium and oxygen, and they both have 2+ and 2- charges. All right? And because their charges are greater and the distance is relatively smaller than these, it's going to have a much stronger bond. And it's going to take a lot more energy to break this apart. So if you think about sodium chloride, lithium chloride, and magnesium oxide is going to have the highest temperature it takes for it to melt or to change phases, because these bonds are really strong. This would be kind of in the middle, and this would be the weakest. So you can kind of make predictions based on their distance and the size of their charges and how they behave. I think magnesium oxide, it takes, I think, over 2,000, 2,500 degrees for it to melt, while salt takes about 800 or 900 degrees to melt. Okay, so it takes for it to melt from a crystalline form to into a liquid state. Okay, right? Because if you add energy, these molecules start to move around faster and faster, and then they separate. Okay. All right. Now here again, we're going to talk a little bit about crystals. Okay. And if we look here, we have titanium oxide and calcium fluoride, or sorry, titanium dioxide, and we have calcium fluoride. I'm not going to expect you to understand these, but this right here is an image of a unit cell, and it kind of gives you a description of the types of bonds that are forming between the calcium and the fluoride and what gives it its unique shapes. Okay? These shapes are determined by the bond structures of these different atoms down below. Okay? And then lastly, one of the last common characteristics of ionic bonds is that when you put them into water, they will separate from each other. We have chlorine and sodium in this example, and they will go toward the anode and cathode of these of an electrical system. And what happens is when electric flows through this, these will move toward the positive and negative ends based on their charges. Okay, so that's why when you put I would say a conductivity meter into plain water with nothing in it, it won't conduct electricity. But if you have some salt water in there, it will conduct. But sugar will not. Okay, you'll notice that experiment. I think we'll talk about it in class. But the reason why salt will is because these are charges and they're separated from each other in solution, and then they will go toward each of these metal plates that are charged. Okay. Also, their melting points of ionic compounds is very high compared to the other types of bonds. Okay. So, here's the example. So NaCl melts at about 800 degrees, and magnesium oxide is about 2,800 degrees Celsius. And we know this because of the Coulomb's law based on this chapter. Okay. So at room temperature, sodium chloride, lithium chloride, types of ionic bonds will be a solid, typically. And they will be able to be dissolved in water, and they will conduct electricity across this current. Okay? Those are just some of the characteristics, and we'll talk more about it in class. And if you have questions, read the book and come talk with me. Okay? Thanks again for watching. Until next time.